In the Choose Your Own Adventure lab, we observe the motion of a man conserving energy by jumping on a trampoline. By observing this motion, we will ask if the man violated the conservation of energy using Tracker, VPython, and principles such as Newton's second law and their energy principle to create a model that came out semi-accurate by simplifications and error. To plot the observed motion, Tracker was used. The values are plotted in the y direction with respect to time. From Tracker, some of the initial conditions were generated. The mass of the man is unknown, so I used the average mass of a human male, which is 70 kilograms. The maximum spring compress, or in this situation, elongation, is 1.32 meters. I was able to obtain that value from Tracker by taking the position of the man right before he hit the trampoline and subtracting it from the maximum length of the trampoline stretched while he was on it. The word compressed is used instead of elongation because when we make the model, the spring in the model will be compressed. However, the magnitude of the distance between the relaxed spring length, whether it is elongated or compressed, will be the same because the force applied is the same. The spring constant and relaxed spring length needed to be calculated. When calculating the spring constant, the time it took for the man to make contact with the trampoline was determined to be the period. That time interval was 0.34 seconds, and along with the mass, the spring force was found to be 3,804.7 kilograms per second squared. When finding the relaxed spring length, the force of gravity was set equal to the force of the spring, and using the values given, the relaxed spring length was calculated to be 1.5 meters. So now we have all our initial conditions set, so we can move on to VPython. In VPython, we have the mass of the ball, which represents the man, to be 10. We had to lower the mass of the ball or the mass of the man because the spring constant in this particular code was too weak to handle 70 kilograms. So just to make the motion work and visible, we lowered the mass. The position is 0 and 0 meters, and the velocity is 0 at also a time of 0. Other initialization includes the gravity, the spring constant, which is shown, the relaxed length, which is 1.5, and then L, which is just the spring position, L hat, which is L divided by the magnitude of L, and S, which you will see in the spring force equation to be the magnitude of L minus L0. We also have the energies at the bottom. We have the kinetic energy shown here, U gravitational, which is the potential gravitational energy, and the potential spring energy. And this is while t is less than 0.97 seconds. The kinetic energy, the initial kinetic energy is shown to be K, initial gravitational potential energy shown to be UG, and initial spring potential energy is US. We have F grav here to be the mass times the gravity, the acceleration. We have the force of the spring shown here. And here is Newton's second law as F net equaling the force of the spring plus the force of gravity. We updated the ball or the man's velocity here, and we updated the position here. Here we updated the position of the spring with L, and here the energies are updated. We set our arrow scales here, and also we set our graph to show the kinetic potential, potential gravitational potential spring, and the total energy. Though the spring is attached to the mass, unlike the observation, the program displays oscillating motion of the spring pushing up on the mass as the mass pushes back down on the spring. By Newton's second law, the forces applied are equal and opposite. The kinetic energy, gravitational potential energy, spring potential energy, and total energy are displayed on the graph. The kinetic energy, the blue plot, and the gravitational potential energy, the green plot, are both non-zero, with the object in motion. And the spring potential energy is zero if the spring was detached from the mass. As the object makes contact with the spring potential energy, which is kind of hard to tell from the graph, but it is this yellow line here, it increases. And the kinetic energy and gravitational potential energy decreases. As the spring forces the object back up, the kinetic and gravitational potential energy increases and the spring potential energy decreases. This interaction and trend shows the transfer of energy due to the interaction of forces. The predicted model has an error because the spring is attached to the object when it should be detached to show the true changes in spring potential energy. By observing a man jump up and down on a trampoline, we are able to model his motion by using Newton's second law and the energy principle. He did not violate the conservation of energy if we consider him and the springs of the trampoline to be the system. With the equal forces applied, the energy is conserved.